We're left with one final puzzle to solve. In the previous video, I talked about how to work with vectors numerically, and in the video before that, I talked about how to work with vectors geometrically. And I'm sure you just went along with me like la-di-da-di-da. But how do we know for sure that we always get the same result both ways? What I mean is, I just showed you two ways of adding a vector, so how do you know that each way results in the same vector? Is it even obvious that they would result in the same vector? I'll share with you some intuition using a couple of examples, one example in 2 dimensions and another in 3 dimensions. For our first example, let's try these two vectors given by 3i hat plus 4j hat and negative I hat plus 2j hat. What do these vectors look like on a graph? They're given here. If we want to add these two vectors, we can just use the tip to tail method that we talked about in the geometric video. Also, we can add them numerically by adding each of their components separately. So visually, it looks like these two results are kind of the same vector. In fact, they are the same vector. But why did it have to be that way? Why did we have to end up with the correct result using both methods? The real beauty comes from the fact that when we add vectors geometrically, we are actually adding them component-wise, even though it doesn't look like it or feel like it. Here, I'll show you. If we consider only the x component of each vector and add those up tip to tail, we expect to end up with the x component of the resultant vector. It's a bit hard to see with the x components, but with the y components, it's a lot easier. If we add the y component of each vector tip to tail, we expect to end up with the y component of the resultant vector. These are in fact the correct components of the resultant vector, not by coincidence, but because the visual geometry of the vectors encodes information about the x and y components. Pretty astounding, don't you think? This was right under our noses the whole time and we didn't even notice. It becomes even crazier when we move into 3 dimensions. Imagine we have the following vectors, negative 2i hat plus 5j hat plus 5k hat, and 4i hat plus 3j hat plus 1k hat. Adding them geometrically means using the tip to tail method, and it turns out this does give us the same answer as adding them numerically, but that's only because we're actually adding them component-wise, even in 3 dimensions. Here, let's change our perspective so we can see the x components add up tip to tail. Taking the x component of each of the vectors being added together, and then lining them up tip to tail, it does look a bit awkward, but we see the negative 2i hat is added to a positive 4i hat to produce positive 2i hat, which is the x component of the resultant vector. Here's what it looks like for the y components. We see the 5j hat y component from the first vector, and the 3j hat component from the second, beautifully line up tip to tail to create 8j hat, which is the y component of the resultant vector. And here's what it looks like for the z components, and we see that they add up in tip to tail fashion as well to produce the right component. Assuming none of that convinced you though, another way of looking at it is that if you have a vector, it's really just the sum of its x component, its y component, and its z component. So if we take two vectors and decompose both of them into the sum of their individual components, and then add up those components together in tip to tail style fashion, we end up with exactly the resultant vector. So we see that adding vectors geometrically and numerically are equivalent operations in 1 dimension, 2 dimensions, and 3 dimensions. When we add vectors using the geometric tip to tail method, it's exactly the same as adding each of their components numerically. I have a feeling if I try to show something like this for all of the other operations we went over, this video might get pretty unnecessarily long. So if you're curious, you should try to piece together some examples yourself that reconcile each of these operations in the context of the geometric side versus the numerical side.